Welcome! Today we'll explore the fundamental operations of vectors in linear algebra. Vectors are mathematical objects that have both magnitude and direction, and we can perform operations like addition and scalar multiplication on them. Let's start by understanding what vector spaces are and how we represent them. R2 is the set of all two-dimensional vectors, which we can visualize on a plane. R2 is the set of all vectors with two components, where each component is a real number. We can visualize a vector in R2 as an arrow starting at the origin and pointing to a specific coordinate. R3 extends this concept to 3 dimensions, adding a z component. R3 is the set of all vectors with 3 components, each being a real number. Now let's learn how to add 2 vectors together. Vector addition is performed component-wise, meaning we add corresponding entries. To add 2 vectors, we simply add the first components together and the second components together. Geometrically, we add vectors by placing the tail of the second vector at the head of the first vector. The sum is the vector from the origin to the final point. Let's work through a concrete example of vector addition. Consider adding the vector with components 1 and 2 to the vector with components 4 and -3. We add corresponding components. 1 plus 4 equals 5, and 2 plus -3 equals -1. So our result is the vector with components phi and -1. Next, let's explore scalar multiplication, which scales a vector by a constant. Scalar multiplication means multiplying every component of a vector by the same number. For a scalar c and a vector, we multiply each component by c to get the scaled vector. Geometrically, multiplying by a positive scalar stretches the vector. Here we see a vector doubled in length. Let's see an example with a specific calculation. Multiplying the vector with components 2 and -1/3 gives us 6 and -3. When we multiply by a negative scalar, the vector points in the opposite direction. Multiplying by -1 flips the vector to point in exactly the opposite direction. Now let's combine these operations to create linear combinations. A linear combination takes multiple vectors, scales each by different constants, and adds them together. The general form is t1 times v1 plus t2 times v2, and so on, where the t values are scalars. Let's work through an example that uses both scalar multiplication and addition. Consider 2 times the vector 1, 3, plus 3 times the vector -1, 2. First, we perform scalar multiplication on each vector separately, giving us 2, 6, and -3, 6. Then we add the resulting vectors component-wise to get -1, 12. Let's visualize a geometric interpretation of a set of vectors. Consider the set S of all vectors, where the second component is twice the first component. Every vector in this set lies on a line through the origin. Plotting several vectors from this set reveals they all lie on the line y equals 2x through the origin. 2 vectors are equal only if all their components match. Vectors are equal if and only if their corresponding components are equal. We can only compare vectors that have the same number of components. Let's recap the key concepts of vector operations. Vector addition is performed by adding each pair of corresponding components. Scalar multiplication scales each component of the vector by the same constant. Linear combinations allow us to create new vectors by scaling and adding existing vectors. These fundamental operations on vectors form the basis for all of linear algebra and have countless applications in science and engineering.